First question is how to draw pressure, volume and temperature entropy diagram for Joule cycle or Brayton cycle, which is thermodynamic air cycle. Second question, solve one problem on Joule cycle or Brayton cycle by using different formulas. Let us first understand how to draw pressure, volume and temperature entropy diagram for Joule cycle. As Joule cycle is considered thermodynamic air cycles. That means air is used as a working substance in this piston cylinder arrangement. If we observe this diagram, here is hot body, insulated cap and cold body, which we have to brought in contact to the bottom of the cylinder one by one for different processes. In Joule cycle, two processes are taking at constant pressure and two processes are at constant entropy. So the processes taking place at constant entropy, we will say that it is reversible adiabatic process or isentropic process. Now from these four processes, we will learn how to draw pressure, volume and temperature entropy diagram. We will move for the process 1 to 2. So how to start this process 1 to 2? For that we have to define what is the initial condition of air. We will consider m kilogram of air is enclosed in this piston cylinder arrangement and which is at pressure P1, volume V1 and temperature T1. So we will select one particular point for this. So I will take here point 1 which is having pressure P1, here is volume V1 and here I will select one point and which is at temperature T1. Now this is the initial condition of air. Now what is the process 1 to 2? So process 1 to 2 is constant pressure heating. So here if we observe this diagram, hot body is brought in contact at the bottom of the cylinder and some heat is getting absorbed by the air from this hot body and there is the heating process taking place, but it is at constant pressure. Now we have to show this process on these diagrams. So pressure remains constant, that's why we have to draw here one straight line. So what is happening when the heating process is taking place? So we know that when there is the heating process is taking place, that means this air is getting expanded. So here what is happening when the air is getting expanded? Its volume will get increased. So we have to show the pressure volume diagram, that is pressure will remains constant, that is P1 is equal to P2, but volume will increase from V1 to V2. So I will show here, we will show arrow also and here will be the point 2. So for this point 2 we will show here the volume V2. Now how we can show this process, that is temperature entropy. Now when the heating process is taking place, means what? Whenever the heating process is taking place, its temperature will be getting increased, and as the heat is getting absorbed by the air, its internal energy is also getting increased and there is the increase in entropy. So remember, when the heat is absorbed, then there is the increase in entropy also. So we have to show this, that is its temperature is getting increased and entropy is also getting increased. So we have to show this, here is the temperature T2 and here is entropy S1 and here is entropy S2. So what is the heat supplied to the air? So we know that there is the heat absorbed by the air and what heat supplied to the air. So we have to write this formula in terms of T, because here the temperature is getting increased from T1 to T2. if we observe here, the pressure remains constant. So we will also consider specific heat at constant pressure, that is Cp. So what is the formula? That is the heat involved in during the process 1 to 2, that is Q12 is equal to M, that is the mass of air, Cp T2 minus T1. So this is the formula. So why Cp is used? Because this process is taking place at constant pressure. So Cp is the specific heat at constant pressure. Now we will move for the next process. So next process is reversible adiabatic or isentropic expansion. So again there is the expansion process is taking place. But this expansion process is taking place at constant entropy. That means entropy will remain constant. So what is happening? So we must know what is the effect of expansion on pressure, volume and temperature. Then only we can draw here the next process. So whenever the expansion process is taking place, pressure is getting decreased, volume is getting increased, and what is effect of temperature? That is, as pressure is getting decreased, that means temperature is also getting decreased. So we have to remember, we have to show here the temperature is also getting decreased. So we will show this. Here pressure is getting decreased and at the same time volume, we have to show increase in volume because of the expansion process. So here will be the point 3. So here we will show here is V3 and here is P3. So here P1 is equal to P2. And now in here temperature entropy will remain constant because this is isentropic expansion and we have to show only decrease in temperature. So here 1, 2 and I will show here 0.3. So here S2 is equal to S3 and here is temperature T3. So during this process no heat is absorbed or rejected. Because here entropy remains constant, so only expansion process is taking place. Process 3 to 4, constant pressure cooling. So we have to show this process, that is the cooling process is taking place at constant pressure. So how this process is carried out? So if we observe here, this here is the cool body and this cool body is brought in contact at the bottom of the cylinder, and then what is happening? Because of this cool body, some heat is getting rejected by the air to the cool body and here constant pressure cooling is taking place. Now how we will show this process? So whenever the cooling process is taking place, that means what? But here pressure will remains constant. So as the cooling process is taking place, we know that here we have to show decrease in temperature. And here we have to show decrease in volume because cooling process, that means we have to show here the volume is also getting decreased because of cooling. But at the same time pressure will remain constant because here the condition is that constant pressure cooling. So we have to show that is P3 is equal to P4 and we have to show volume at point 4 should be less than this point 3. So here is V3 and we have to show the decrease in volume, that is I will show here V4. I will show arrow also and here. So P3 is equal to P4. Now at the same time we will show here the process temperature, we have to show decrease in temperature. So what is happening during cooling process for the entropy? So during cooling process entropy is getting decreased. So you have to note down in your notebook, whenever the heat addition taking place entropy increases. When the cooling process is taking place entropy decreases. So we have to show here both, that is decrease in temperature and decrease in entropy. So I will show here. So this point will be point 4 and here will be temperature T4. So here heat rejected by the air. So what is the amount of heat rejected? So during this process 3 to 4, if we observe this process is taking place at constant pressure, so we will consider specific heat at constant pressure, and here decrease in temperature from 3 to 4, that is T3 to T4. So Q34 is equal to mCp, difference in temperature, that is T3 minus T4. Then process 4 to 1. So this process is reversible adiabatic or isentropic compression. As we know that this is the compression process taking place at constant entropy. So what is happening during compression? During compression process, pressure is getting increased. Then volume is getting decreased. And what about the temperature? So as pressure is getting increased, its temperature will also getting increased. So we have to show all these processes. So here we have to show from 4 to 1 pressure is getting increased. So if we observe here already, that is P1 is greater than this P4. Then we have to show decrease in volume. So here this volume at point 1, that is V1, should be less than V4. So we have to select point 4 in such a way that V1 should be less than V4. So I will join these 2 points and I will show arrow also. So here is this process. Now here temperature, we have to show increase in temperature but constant entropy. So we have to draw straight vertical line. And here S1 is equal to S4. No heat is absorbed or rejected in this process. Let us understand some formulas with the help of diagram. So for the Joule cycle, what is the work done? So we know that work done means heat supplied minus heat rejected. So heat supplied is during the process 1 to 2 and the heat rejected during the process 3 to 4. So these two processes are taking place at constant pressure. So what is the formula? That is mCp T2 minus T1 minus mCp T3 minus T4. Now we will move for the next formula, that is efficiency. So efficiency means work done by heat supplied. So this work done, we will write this whole formula, and heat supplied, that means we have to take what is the formula during the process 1 to 2. So mCp T2 minus T1 minus mCp T3 minus T4 divided by mCp T2 minus T1. So we can take here mCp as a common term, and in numerator and denominator it will be getting cancelled. So what is remaining? That is, if we simplify this, we will get 1 minus T3 minus T4 divided by T2 minus T1. So we can use this formula. Then we will move for the next formula. If we observe here, the process 4 to 1 and 2 to 3 is taking place at constant entropy. That means there are two processes that are isentropic processes. So how we can write the formula during these isentropic processes? So for isentropic processes, we will consider isentropic index, that is gamma. And this gamma, how to calculate? That is nothing but the ratio of specific heats. So specific heats, that means Cp and Cv. Specific heat at constant pressure Cp, and specific heat at constant volume, that is Cv. So this gamma is equal to Cp by Cv, which is known as isentropic index. And this is used only when the process is isentropic, that is during the process 4 to 1 and 2 to 3, this gamma is used for the different formulas. Now we will understand what are those formulas. So here T3 by T2, that means the temperature during the process 2 to 3 is used. So T3 by T2. So during the process 2 to 3 it is isentropic process. So ratio of T3 by T2, which is equal to, now we have to write this formula in terms of volume V and pressure P. So how we can write this? So for that we will use this gamma. In terms of gamma we will write these formulas. So T3 by T2 is equal to V2 by V3 raised to gamma minus 1 is equal to P3 by P2 raised to gamma minus 1 by gamma. So these formulas are important. So how we can calculate this T3 and T2? So for that we have to either know the ratio of this volume and value of gamma, or we know ratio of this pressure and the value of gamma. Now in the same way we will move for the next isentropic process, that is 4 to 1. So here is also formula, that is ratio of T4 by T1. So T4 by T1 again we will write in the same way, that is V1 by V4 raised to gamma minus 1, which is equal to P4 by P1 raised to gamma minus 1 by gamma. Now we will again observe all these formulas. If we observe here, this pressure P3 which is equal to pressure P4. So I can write here which is equal to P4. Instead of P3 we have to write here P4, and this pressure P2 is equal to pressure P1, that is divided by P1 raised to gamma minus 1 by gamma. So if we observe, here is also P4 by P1 raised to gamma minus 1 by gamma. So we can equate all these, because here P3 is equal to P4 and P2 is equal to P1. So we can say that here V2 by V3 raised to gamma minus 1, which is equal to V1 by V4 raised to gamma minus 1. We can also say T3 by T2, which is equal to T4 by T1. So all these relations we can use while solving the problems. We will solve one problem. I will read what is the given question. An air motor works on Joule cycle between 5 bar and 1 bar. The temperature at the beginning of isentropic expansion is 773 Kelvin and at the beginning of isentropic compression is 293 Kelvin. Determine the work done per kilogram of air and ideal efficiency. Assume Cp is equal to 1 kilojoule per kilogram Kelvin and gamma is equal to 1.4. Let us understand the given data. Now this cycle is Joule cycle. That means there are two processes that is taking place at constant pressure and two processes at constant entropy. Now pressure range is given. So pressure range is given 5 bar and 1 bar. So if we observe this pressure volume diagram, then 5 bar is the higher pressure, that is P1 and P2 is higher than this P3 and P4. So we can say that P1 is equal to P2 is equal to 5 bar and P3 is equal to P4 is equal to 1 bar. So we have to write that. Then the temperature is also given. So temperature at the beginning of isentropic expansion. So when expansion process is taking place, so if we observe here this diagram, then the process 2 to 3 is the expansion process that is taking place at constant entropy. So at the beginning of isentropic expansion, that is at point 2. So this temperature is given in Kelvin, 773 Kelvin. And the temperature at the beginning of isentropic compression. So here isentropic compression process is 4 to 1. So at the beginning of isentropic compression, that is temperature T4 is given 293 Kelvin. Then the specific heat at constant pressure is 1 kilojoule per kilogram Kelvin and gamma is 1.4. Now we have to calculate what is the work done. So how to calculate work done? So we know that work done is equal to heat supplied minus heat rejected. That is mCp T2 minus T1 minus mCp T3 minus T4. Now if we observe here, T2 and T4 are known. So I will mark out that here is T2 and T4 is known, but T1 and T3 both are unknown. So we have to first find out this temperature. So we know that for isentropic processes, that is for expansion process as well as compression process, we have to use the gamma term and we have to write the formula. Now we can write the formula to find out the temperature during these isentropic processes by using ratio of pressures and ratio of volume. But in this question pressure is given. So we will use here the pressure ratio. So now for this isentropic expansion 2 and 3, that is T2 and T3 is involved. So how we can write this? So T3 by T2. So we will take the ratio T3 by T2 is equal to. Now we will use the ratio of pressures, that is P3 by P2 raised to gamma minus 1 by gamma. Now P3 is 1 bar and then P2 is 5 bar. So we will write 1 by 5 raised to 1.4 minus 1 by 1.4. So when we calculate, we will get the answer 0.6311. Now we have to calculate T3 because T2 is known. So T3 is equal to 0.6311 multiplied by 773, which is equal to 488 Kelvin. Now this value is in Kelvin, so answer will also in Kelvin. Now we will move for the next ratio, that is for this isentropic process T4 and T1. Again we will use the pressure ratio. So T4 by T1 is equal to P4 by P1 raised to gamma minus 1 by gamma. So what is P4? That is 1 and P1 5. So 1 by 5 raised to gamma minus 1 by gamma. So if we observe, here is the same ratio is there. So answer will be same, that is 0.6311. Now we have to find out temperature T1 because T4 is known. T4 is 293. So we will take here T1 is equal to 293 divided by 0.6311. So which is equal to 464 Kelvin. So in this way, this T1 is there as well as T3 is there. Now it is easy for us to put the value of this T1 and T3 in this formula and we can easily calculate. Now if we observe here M and Cp is the common term, so we can also take common. So what is the value of M? So here mass of air is not given, so we have to take it as a 1 kilogram. Because specific heat is given 1 kilojoule per kilogram Kelvin. So we will use here this Cp value is 1 and M is also equal to 1 and T2 minus T1, that is 773 minus 464 minus 488 minus 293. So when we calculate this, we will get the answer 309 minus 195, that is equal to 114 kilojoule. So this is the value of work done. Now how to calculate efficiency? So we know that efficiency neta is equal to work done divided by heat supplied. So what is the value of heat supplied? So heat is supplied during the process 1 to 2. So heat supplied is equal to mCp T2 minus T1. So if we observe mCp T2 minus T1, if we calculate this, it is 309. So work done is 114 divided by 309. So we have to find out this answer and that will be efficiency. So if we multiply this answer with 100, then we will get the efficiency in percentage.